Let us examine the rocks we have from our kit. Numbers 1, 2, and 3 are felsic. They're intrusive. And why? Why are they felsic? Because they're light in color. Some of them are peppered with a few dark minerals, but basically they're light in color. And you can see the crystals. They would be granites and cyanites. And you needn't worry about distinguishing between them. The fourth rock is a gabbro. Obviously it's dark in color. And it has mostly iron magnesium minerals and some feldspar that is darker in color. Now we don't have an example of an intermediary between a gabbro, mafic, and felsic, the granites, which would be a diorite, which would have maybe half dark minerals and half light minerals, half mafic and half felsic. Number 5 is the extrusive equivalent of a granite. It's a rhyolite or a felsite. It's light in color. It has a few flecks here and there. Now those are phenocrysts. It's called a porphyritic texture because when this magma started to cool and crystallize, it was below the surface, so it was cooling slowly, and these little crystals had a chance to start forming. But then it was raised to the surface and cooled rather quickly, so the rest of the matrix is made up of crystals that are very, very small and hard to see with the naked eye. This would be a rhyolite porphyry, or a felsite porphyry, number 5. Number 6 is a basalt. At the other end we have the extrusive equivalent of a gabbro, but it is extrusive, so we can't see the crystals. Notice the gabbro, we could see the crystals, see the grains interlocking, but we can't see that with the basalt. Now the next two are extrusive rocks, but this one cooled so quickly that it didn't have time to crystallize at all. And even though it's dark in color, it is a felsic rock made up of silica and some of the feldspar ingredients, but no crystals. And it is black or very dark in color and has curved fracture. And the other extrusive rock, which is unusual, is riddled with vesicles. These are holes. They were gas bubbles. It solidified very quickly, and the gas bubbles remained intact in the specimen, in the rock, and it is very light because it is mostly air in there, and it will float. It's one of the few rocks that will float in water. Those 1, 2, 3, 4, 5, 6, 7, 8 rocks are igneous. Now we go to the sedimentary rocks. We first look at a conglomerate, and it is large. The pebbles here, the grains are larger than sand grains, and they're cemented together. The British call this pudding stone, and if these grains were really angular, we would call it a breccia. But this sample is a conglomerate, number 9. Number 10 is a sandstone. It happens to be the Berea sandstone of Ohio, and it is made up of sand grains. If we look with the hand lens, we could see the individual sand grains that are cemented together. Then the next is made up of clay minerals that got compressed. Okay, and it is a shale. Don't Don't call it a slate. That's a metamorphic equivalent. We'll get to that soon. It is thinly bedded. That's why we call it a shale. And it is made of clay minerals that have been compacted together. Sometimes you can see small plant fossils in your specimens. The next one is a limestone. Now, a lot of limestones are white or very light in color. This happens to be a very dark limestone. The one after it is a dolomite, which instead of being calcium carbonate like the limestone, is calcium magnesium carbonate. And it is, both these were chemically precipitated. Whereas the shale, the sandstone, and the conglomerate are clastic sedimentary rocks, which broken and then cemented together. Whereas this, the limestone and the dolomite, were precipitated from a solution. The next rock is called chert, and it characteristically banded, has a reddish or maroon band with some gray and tan bands. It is basically quartz again. That it is slightly crystalline, what's called cryptocrystalline, and it is very hard, and again it's called chert. That's number 14. And the next rock is gypsum rock, again precipitated out of a solution, and it is made up of the mineral gypsum, but not good crystals of gypsum. They're all a mass of gypsum here, and it is used for drywall. So this can be mashed up and put into drywall. Then those are the sedimentary rocks, the numbers 9, 10, 11, 12, 13, and 14. Then, and 15. And then we go, starting with 16 through 20, these are metamorphic rocks. This is a quartzite, number 16. It is a metamorphosed sandstone. And don't let the color fool you, there's just iron staining there. But these individual grains that had been cemented together have now been pressed and heated so that way down in the depths of the earth and recrystallized to these quartz grains are interlocking now, not just cemented by a cementing medium. The next one, which is number 17, is a slate. It's the metamorpho equivalent of shale. It's a bit shinier and it won't have fossils. The next one is a marble, a little hard to get out of here because of the nature of the box here. And it is a metamorphosed limestone. Again, don't let the color fool you, but this, you can see that the crystals have come out again. They're interlocking calcite crystals into a metamorphic rock, good for sculpturing. Then the following rock is number 19, which is a schist. You can see the mica that has come out of maybe a metamorphosed slate, and there's an intermediate which we don't have a sample of, which is called phyllite, which shows some of the platiness of a schist, but not quite as much. And the clay minerals have been turned into mica. This is a mica schist, and what happens is when heat and pressure are applied, the mica flakes form and line up in planes called foliation. That is the mica schist, number 19. And then finally, number 20 is a gneiss, G-N-E-I-S-S. It has that foliation, the banding, very finely banded here, but it is the ultimate of the metamorphic process without having to melt the entire rock and then form an igneous rock. Let me show you, this is one example. It's a darker colored example, but let me show you two other specimens, larger specimens, that this one is a granite, and has the pink feldspar, the orthoclase feldspar. It has nice big hornblende crystals in here, and it has some quartz. Hard to pick out, but they're the kind of glassy material that is a bit cloudy, and that is a granite. It is an igneous rock produced by solidifying from a magma. But if it's metamorphosed, it now looks, it has the same minerals, but it is now banded, foliated in these layers where the minerals are now lined up in planes. Which this is a gneiss, this is a granite. See, this banding isn't as, it is more dominant than the kind of banding we see in the sample that you have, in the specimens that you have. Also, let me show you another example of a shale, because the shale doesn't have to be black. This is the shale, and here is a specimen of shale that I collected on the one of the Orkney Islands north of Scotland, and you can see it's thinly bedded. It's got that layering, but it's not all black. It is dark in color. Shales can be red, they can be green, they can be gray, they can be black, so that don't let the color fool you. That is the shale. Now, another example of a sandstone. Remember, we saw the Berea sandstone. That was light in color. Also collected on the Orkney Islands when I was there is the old red sandstone. Has a reddish color to it, and is one of the first rocks that were studied back in the 1700s by the first geologists, actually. And again, it's made up of sand grains, and the reddish color is from oxidation of iron cement or coating on the sand grains. And then one other rock I want to show, well, two other rocks. This one is another limestone. You can see it's kind of dark gray or black in color, and it has a trilobite fossil. I don't know if you can make that out. It's put some material on it to bring out its shape, and it is one of the segmented life of the early Precambrian, this one, and it is about, several hundred million years old. This would be preserved on limestone. We know it's a sedimentary rock when we see the fossils, because in an igneous rock or a metamorphic rock, the fossils would be destroyed by the process of melting or metamorphism. And then one other rock that I collected in Hawaii and this has a ropey texture to it because it was so viscous. It started to flow and solidify, and lots of gas bubbles formed vesicles in the rock. This was warm when I collected it. It had just been extruded from the volcano called Kilauea on the Big Island of Hawaii. And this kind of texture is called pahoehoe, a Hawaiian term for this ropiness of the lava. And I lied. I do want to show you a couple more rocks outside your collection. And here's another example of chert. can see the banding and the color. And here's another limestone with brachiopod fossils. And let me see if I have another one. Well, this is just, here's another example of obsidian, the glassy rock that has solidified so quickly on the surface that it didn't have time to crystallize at all. Just formed a glass obsidian. And here's another fossil I collected, which came right out of the rock. It's a brachiopod and very well preserved, about 350 million years old. This would have come out of a sedimentary rock.